With our steady state tuning, we're going to essentially repeat what we looked at with our fuel steady state tuning, and we're going to be starting from low RPM and low load, and we'll be working our way up through to around about 2/3 of the engine rev limit. So on this basis, we'll be starting around 1500 RPM, down around about 40 to 60 kPa, essentially as low as we can get. Now, there are a few things we need to consider. First of all, how are we going to do this? With the torque optimization test that we just looked at, it's going to take forever if we were to tune every cell in that way. So instead, what we're going to do is use the torque feedback function on the dyno's main screen. So let's have a look at that now. First of all, we've got two ways of doing this. The top of the screen, we've got our actual torque gauge. So this will give us a real-time indication of the torque, as well as a numerical display of the torque value as well. This is useful, but I personally find that it's quite tricky to see the small adjustments or trends that we're going to be expecting to see in our torque from this. Instead, I prefer to use the gauge down below. So this gives us a real-time trace of our torque in red, and our ignition time is actually also being displayed in yellow. What we're going to be doing here is getting the engine to a steady state equilibrium condition, basically looking for a point where the torque is as stable as we can get it. We're going to make a change to the timing, and we're going to see what effect that has on our torque. So it's going to be essentially the same as our MBT test or torque optimization test we looked at, but we're just going to be using a different input to guide us with our tuning. Another consideration we need to have here is that, particularly when we first get started at low RPM and light throttle, we may struggle to see the sort of changes in torque, particularly if we're operating right on the lower limit of the load cell's reading capability. So this is something we need to bear in mind, and sometimes we're going to need to interpolate some of the results we see with a little bit more load on the engine down into those lower load regions. Now we understand what we're going to be doing. Let's get up and running, and we'll start again at 1500 RPM. Alright, we'll just get ourselves into the middle of the 1500 RPM column here and get ourselves as low down in the load as we can. And get into the middle of that 60 kPa zone quite easily, but just like with our fueling, as we reduce the throttle down, we're not actually going to be able to get into the 40 kPa cell. So the first cell we're going to start with there is our 60 kPa cell. Okay, let's have a look over at our torque graph, and we're reasonably stable at the moment at about 120 to 125 pound-foot of torque. Again, of course, the torque is moving around, so what we want to do here is make a change. We're going to try advancing the timing to 12 degrees, so I'll enter a value of 12. And what we want to do here is just, again, make sure we're in the center of the cell, or as close to as we can. We will look at our torque before and after we press enter. So we'll press enter now. We'll see our yellow value for our torque jump up. Now looking at that, we've really seen almost no noticeable change, definitely no perceptible change in our torque graph. Just to confirm that, let's go and take 4 degrees away, so 2 degrees below where we started, to enter a value of 8. Again, just making sure everything's nice and stable here, make sure we're as close to the center of that cell as we can. We'll press enter. Now we have seen our torque drop away. So let's go back to our starting point of 10 degrees. We'll press enter, and we do see our torque jump up. So it looks like that our base value that we had in there at that cell was actually pretty much on the point there. We're pretty much right on MBT at 10 degrees, so a drop off at 8 degrees. Now, should we retard the timing at this point? 1500 RPM and 60 kPa, no load really, so to speak. So our chances of detonation under these conditions, very, very remote. So I'm quite happy to leave the timing where it is. What I will do though, before we go up to 80 kPa, I'm going to highlight the cells higher in the load from where we are, lower in the map, which is a little confusing, and we're just going to remove 2 degrees from those cells. The reason for this is, as we increase the load, we expect our timing to want to retard. So now let's increase our throttle position. We'll come up to the center of our 80 kPa site. Right, we're stable in the center of that site, looking at our torque there. Over that to stabilize, we're around about 260 to 270 pound-foot of torque. So let's try increasing our timing from 8 degrees to 10 degrees. We'll press enter now. No perceptible change really, a little bit of a bobble in our torque, but really nothing to speak of. So let's go back to 8 degrees, and naturally we don't see the torque reduce there. Now let's see how close we are to MBT. We'll go to 6 degrees here. And again, we actually don't really see any reduction in our torque at 6 degrees. To just confirm that, let's go to 4 degrees. Okay, with 4 degrees we do see our torque drop off. So let's go to 6 degrees. So here we can just see how quick and easy it is to actually find the optimal ignition timing value. So again, now that I have retarded that timing, I'm going to highlight those cells above, and we'll bring that back to 4 degrees for our next site, which is 90 kPa. Let's come up to the center of that site there, 4 degrees. We'll wait for our torque to stabilize, 330 pound-foot of torque, relatively flat there. So let's try advancing our timing up to 6 degrees. We see a small improvement there, but not really that significant. So again, for the purposes of safety, actually retard that back to 4 degrees. I'm really not concerned about the small change in torque that we saw there. So let's just again make some adjustments to our timing values here, just on the basis of the trends that we're seeing. We always want to retard our timing as we move into higher load regions. So we'll come up to 100 kPa here. At the moment, the value there, 2 degrees. See what our torque's doing. Nice and stable there at about 400 pound-foot of torque. So let's try advancing our timing up to 4 degrees. Small improvement, but really insignificant. So we're right on that beginning edge of the plateau for our torque MBT timing. So I'm going to leave that exactly where I am. We'll go through to wide open throttle. We can't quite get to 120 kPa, 0 degrees in that. So I'm actually going to leave that exactly where it is. So let's come back to idle and we'll have a look at the results that we've got here. So first of all, we've got 10 degrees in this particular cell here, the one that we could tune. And we know that our trend is going to be that as the manifold pressure reduces, the load reduces, we are going to find that our timing will probably need to advance a little bit. Now, I'm not going to be too worried here, and likely given how close we are to MBT, or that plateau for MBT, we're not really going to see a significant change there. So I'm not going to be too concerned here. If we want to just follow the trends we're likely to see, we could enter a value there of perhaps 12 degrees, and we can then use the vertical interpolate function there to interpolate between those cells. You can do that by right clicking and using the interpolate columns function, or alternatively press Y. Not strictly necessary, we're really not chasing that last pound-foot of torque there, but this is the sort of trend we're likely to see. Right, with our 1500 RPM column tuned there, what we're going to do is click on the 1500 RPM label. It'll highlight the entire column. Control C, right arrow key will move us across, and then Control V will copy that to the 2000 RPM column. Now, we're not going to advance our timing at the moment. We always want to start from a position of retarded safe timing. So let's get ourselves up and running on the dyno again. We'll increase our set point to 2000 and we'll repeat that process. Alright, we're up and running again now at 2000 RPM. Again, 60 kPa is the lowest load cell we can get to. We've got 10 degrees in there at the moment. So what we're going to do, we'll look at our torque. We're about 140 pound-foot of torque. So we'll increase that by 2 degrees. We're looking for the trend in our graph. We do see our graph does jump up. We're up to about 146, 147 pound-foot. So the engine does want a little bit of additional timing at that point. So let's go again. We'll go to 14 degrees here, again looking at our trend before and after. Now we see again our torque graph does jump up. We're up to about 150, 152 pound-foot at this stage. So it's like the additional timing there. Again, we'll add another 2 degrees looking at our torque before and after. Again, we do see our torque jump up. Again, remembering here, very light load, so I'm not too concerned about any chance of detonation. So we can be a little bit closer to MBT under these conditions. Let's try another 2 degrees. We'll go to 18 degrees and see the effect of that. 18 degrees now, really almost no perceptible change. So what we're going to do is come back to 16 degrees here. Now I'm just going to essentially extrapolate those results out to the higher load, or lower load areas I should say, the lower vacuum areas that we can't get to. Let's come up now to our 80 kPa cell. We've got 6 degrees in there at the moment. Chances are that's going to be quite conservative given the trend we've just seen. So let's see, we're nice and stable there on our torque at about 275 to 280 pound-foot. Let's try entering a value of 8. We'll press enter, and we see our torque line does increase. So let's go again. We'll enter a value of 10 again, just waiting for our torque to stabilize before we press enter here. Press enter. And again, our little red line for our torque does increase. Not a significant increase this time, but an increase nonetheless. And we'll wait for it to stabilize. We'll try 12 degrees here and see what happens with 12 degrees. Again, 12 degrees, we've seen an increase in our torque. This is in line with what I'd expect there, just given the numbers that we've seen above there. So 16 degrees at 60 kPa. So I'll try 14 degrees and just see the effect of that. 14 degrees, really no change, so we'll come back to 12 degrees. All right, coming down to 90 kPa here. Again, 4 degrees at the moment, expecting that's going to be pretty conservative. So let's see what we've got there. Wait for everything to stabilize. 345 to 350 pound-foot of torque. So let's go to 6 degrees for a start. See that our torque does increase, but not significantly. Let's try another 2 degrees here. We'll go to 8 degrees. And we see that our torque does jump up there, again, only marginally. So we can try 10 degrees, but probably just going to come back here to 8 degrees. It's really not really showing any improvement there, so the additional timing not really worth having. We'll just make sure that we are central in that cell. Again, I just noticed we had reduced our engine manifold vacuum a little bit, so I just want to really be sure that I am central on that cell, because that can influence our results. So let's have another look. 355 to 360 pound-foot. Let's just try 10 degrees again. Yeah, there's really no difference there, so I'm going to go back to 8. All right, we'll come up to 100 kPa here. 2 degrees at the moment. Looking at our torque, 415 to 418 pound-foot. Let's try increasing our timing to 4 degrees. We see our torque does pick up there. We'll go again to 6 degrees. Our torque does pick up there at 6 degrees. So let's just try 8, even though I'm not expecting that will be the case. 8 degrees, we actually do pick up again. So let's just try going there to 10 degrees. Press enter now. 10 degrees, we've actually still picked up a little bit there. So this is where we can highlight a potential hole in our map. So we've got 12 degrees at 80 kPa, we've got 8 degrees at 90 kPa. So under these circumstances, what I'd be inclined to do is come back to our 90 kPa cell and just check again and see if we do actually see an improvement. I'm expecting that the timing there should probably be closer to 10 to 11, just following the trend that we are seeing. So let's try again. We'll look at our timing there, sitting at about 365, 370 pound-foot. Press enter, and we actually do see a very small increase in our torque there. So I'm just going to go and split the difference there, hit 11 degrees. Can't really notice that difference of 1 degree, but just to follow that trend. All right, let's come up, and we can actually get into our 120 kPa cell now. So now we're holding a bit of load, so we do need to be a bit mindful. So let's move a little bit quicker here. We'll try 2 degrees. See an improvement there from 2 degrees. Let's try 4. Another improvement with 4. We'll go to 6 degrees here. Okay, 6 degrees. We saw an improvement, but a very small one. We'll just try 8. And again, a small improvement, but what I'm going to do again, just to be on the edge of the MBT plateau, I'm going to set that to 6 degrees. So 120 kPa, essentially about as far as we can get at that particular point. What I am going to do though, just for the sake of completeness here, is we'll copy that trend down, and we're going to enter a value of 2 degrees at 140 kPa. All right, so that completes our 2000 RPM column. What we're going to do is, again, Control C and Control V. We'll copy that across to 2500. We're now going to repeat the process. What we do need to be mindful of here is that we don't want to be holding the engine under sustained high boost once we get higher in our RPM range, because we're going to be creating a lot of heat quite quickly. So this is where we also need to understand that we will be optimizing the high boost areas, so our wastegate, spring pressure and above, if we're increasing the boost during ramp runs. So we don't need to be too specific there, and this can be a bit of an iterative process process. Once we've done our ramp run tuning and we've got our wide open throttle ignition timing areas dialed in and optimized, we can then come back and look and see if we need to fill in any of the areas between our 120 kPa up to the 200 kPa that we are going to be running. So there's no point, we don't need to really put the engine under undue stress and strain trying to be really precise in those areas between sort of our wastegate spring pressure, 200 kPa in this instance, and the sort of 120 kPa area that we're going to sort of generally be operating in under steady state conditions. The other reason we don't need to be so precise with this is because as we increase our throttle, we're going to be transitioning through those very quickly. So if we're not right on MBT, it's not essentially going to be that critical. All right, let's carry on with the process now. Right, at this point we've got our ignition timing steady state tuned up to 4,500 RPM. You've noticed that I've essentially gone up to about 120, 140 kPa, so I'm not trying to get through to full boost there for the purposes or the reasons that I stated already. We're just filling ourselves out into the positive boost areas. Most interested with the steady state tuning, really again just on the areas that we truly will be operating under steady state condition. Now also particularly down in the lower load areas, we start to see that we kind of reach this plateau again, a little bit unlike a piston engine where we will see quite a sharper trend in terms of more ignition advances, our engine RPM increases. It's not quite so much the case there, and the rotary engine tends to be a little bit flatter. So we've got timing values out to, in this case I've extrapolated out to about 160 kPa. However, we know that we're going to operate up around this 200 kPa region with our, if I can just highlight the 200 kPa row, with our 1-bar spring that's in our wastegate. So we know that we haven't got down there, and again there's no need putting undue stress and strain on the engine, running it at a 100 kPa of positive boost steady state for a long period of time. Going to create a lot of unnecessary heat, stress and strain. We're going to do this under ramp runs, which we'll look at in the next segment. So at this point I'm happy with the numbers we've got in here, and again we may come back and address these and see any trends that we've developed once we get up to 200 kPa, exactly what the engine wants. Do still have a little bit more work ahead of us though. What I'm going to do is start by copying our 4,500 RPM column, and we'll just copy this out using Control C and Control V all the way out to 9,000 RPM. And again, we can rightly expect that our actual timing will probably increase a little bit with RPM, but for now we're going to leave that where it is. We do also have a little bit of an area of inconsistency down here between 1000 RPM and 2000 RPM. Remembering we couldn't steady state tune at 1250, 1000 RPM, and we've got this area where our timing is a little bit inconsistent. So not strictly a problem, but just for the sake of completeness, what I'm going to do is just smooth those values. So what we'll do is start by highlighting from 1000 RPM to 1500 RPM. We use the X key there to interpolate, and then what we'll do is we'll just set all of these cells here to 4 degrees and all these cells here to 2 degrees, just again for the sake of completeness. It's not an area we're going to be operating in, just for the sake of having a relatively smooth and consistent trend in our table. So at this point our steady state ignition timing has been completed. We're going to move on with the next step of our process.